I've been learning and working with software-defined networking technologies for a few years now, and I hope that today's presentation you'll benefit from the research that we've done in this technology sector. A few logistical things this morning. You'll all get a copy of the slides when we're finished today, so don't feel like you have to write things down furiously. Listen. As you listen to me talk about these concepts and ideas, think about questions you'd like to ask. You can enter those questions into the chat window, and I'll see if I can work them in, but I'm monitoring that chat session. We're going to record today's session, so if you have to step away, you get a phone call, you can watch the replay, and we'll make sure you get information about how you can view that. With that, we'll go ahead and get started. Talk about just today's agenda. We'll go over a high-level, just kind of introductory view of what software-defined means, what the concept is, describe the business benefits that organizations would get from a software-defined networking system, or what are the problems that SDN are trying to solve that we have today in our network environment. And then talk about use cases, like how are organizations using software-defined networking to achieve these business benefits. We'll review the industry organizations that are involved in software-defined networking, and then talk about, honestly, like what are some of the challenges, objections, problems with software-defined networking and how we overcome those. And then an industry outlook, what do we expect to see in the software-defined networking world in the coming year or so, as far out as you can try and predict anyway. We'll talk a little bit about GTRI solution methodology and our services, but that's really kind of what we're going to cover. Today is really an introduction to software-defined networking. You'll see that GTRI is going to put together a series of these web seminars on software-defined networking, a variety of different SDN-related topics. So we'll be having about one of these every month or so. So look on the GTRI.com website on our events page to see the current things that we have coming up. So with that, as Bob Dylan so predicted back in 1964 when he wrote the song, "The Times They Are a-Changin'." I mean, we're in this time in IT infrastructure where things are moving quite rapidly. We've had a lot of years where we've had very stable IT environments with very stable use of technology, and now we're in this movement towards virtualization, multi-tenant, cloud, moving to third platform, bimodal IT, consumption economics. They're really influencing how organizations are thinking about and deploying IT infrastructure. And really software, as Marc Andreessen said in the Wall Street Journal article a bunch of years ago, software is eating the world. We also see DevOps, this rise of the DevOps concept and practice of combining development and operations. It's not just a digital age portmanteau where we take two different words and stick them together. It's really this movement of IT de-siloization and getting groups to work together cross-functionally that's driving a lot of innovation and speed. DevOps is this concept of using, continuous integration, continuous development and testing and creating new software and rapidly accelerating time to market of applications and systems. And this is coming to networking too. We kind of want to move from very statically defined networks to software-driven environments. And here are a few books that you might be interested in reading that kind of talk about these. The Phoenix Project really being the key book when it comes to describing the concept of DevOps. So I highly recommend you read that book if you haven't read that. And it really is pretty eye-opening for someone, a network engineer, network administrator, security administrator, and you see yourself and identify with the characters in the story of the book and go through that journey of moving to a DevOps environment. So there are many benefits of virtualization in software. We've seen how servers have transformed from bare metal systems where there was really one operating system on one server and multiple applications on that one physical server. Now applications are virtualized, they're moving to containers. We see storage systems evolving from where it was a physical device to now using more software features, virtualizing the storage, de-duplication, replication, automation of storage to match the compute environment, and all of these things moving to cloud environments, and so geography is less meaningful. But networking is starting to become influenced by this software movement, but really networking hasn't changed that much in 15 years. You know, we still manually configure network devices with a static configuration stored in non-volatile memory in case the router reboots or switch reboots. They're configured one at a time by a person. And so this doesn't lend, this convention of manually configuring networking devices doesn't lend itself well to automation or configurations that change or are dynamic as the business changes. You kind of set your QoS policies, set other policies on these network elements manually, and they don't change for even a year or so, but yet your business applications have changed and are changing quite rapidly. But so the network can be a bit out of sync, but then also, on the other hand, networks need to support all the various applications that ride across them, so they kind of have this requirement to be the lowest common denominator and support all applications, but we don't have the ability to influence application traffic, and really IP networking routing protocols forward packets based on the way they've computed a best path based on some metric, distance, hops, what have you, AS path, bandwidth. And when they pre-compute a single direction to forward traffic, that's the path that all the packets take regardless of the application needs. There's a disconnect between what the application desires and the application performance and the end user experience and the way the network has been, configured manually and computed the best path. So IP routing protocols don't take into account application requirements or current traffic load. They really, base their decisions on empty number of lanes of traffic, going from point A to point B based on routing by rumor type information that they receive. Network administrators have only managed to move from Telnet to SSH. That's their only transformation in the last 15 years. And so many network engineers are curious about this concept of software-defined networking. Here's a funny cartoon created by Klossner. Greater agility, faster deployment, simplified architecture, whiter teeth, brighter, all these things. He says, I don't want to invest in the technology, I just like to invest in the hype. And certainly I think SDN, can mean different things to different people, and software-defined networking at this point kind of seems like cloud and other terms in IT that tend to be overused and thus tend to lose their meaning. And everyone kind of views software-defined from their own particular perspective. A security administrator might think of software-defined networks from one perspective. A system or storage administrator or network administrator might view SDN in a different way. But kind of getting back to the textbook definition of software-defined networking, it's really an approach to networking, a new paradigm for networking, to use another overused term, that separates control from data plane. In the past, we've had network devices where the control plane and the data plane are in the same device. So the same device that's forwarding packets is also along those same paths sharing control traffic, typically IP routing protocol information about reachability. And then each of those routers, based on what they hear from their neighbors, then forms a topology in and of themselves that determines the forwarding table. There's a routing table and a forwarding table, and that's how modern or today networks work. But the control plane is integrated into the network device. With software-defined networking, we're going to separate out the control plane and create kind of a central brain of all the forwarding intelligence. And then that central brain that runs the control plane will then have more of a global view of what's taking place on the network and then get inputs from applications to decide how packets should be forwarded to maximize the use of the network. And that central control function can make more intelligent decisions about, how to handle network traffic and, can be more in line with the application and be more dynamic. And then that control plane can then enforce forwarding based on network elements in the environment. So here's kind of a high-level architecture. And software-defined networkings most of the time have these common 3 layers. We have a low layer of the physical network elements, and we have this disaggregation where we've disaggregated the control plane from the forwarding. We've disaggregated the ASICs. We've moved back to a point where the network elements are more commodity devices using merchant silicon, commodity, hardware, and have less intelligence in the network element. But now we've taken a lot of the intelligence and put it into this control layer, this controller layer. So you have, below, you have this data plane layer, infrastructure layer as it's sometimes called. In the middle, you have a control plane, a control layer, where we have all that control plane functionality. This is the brains of how forwarding takes place. And then up above that, we have applications and other types of software that might, and policy and design information that then, is imparted upon that controller. And we can have redundant controllers, and the network elements can be cabled up and connected, to physical server environments or logical. The network element doesn't have to be a physical device. It could be a virtual switch, could be a virtual switch that's extended to a cloud environment, could be a data center interconnect type virtual switch using some protocols like VXLAN or OTD or some other types of data center interconnect protocols, NVGRE, others. And so we have the kind of this 3-layer model, but some SDN systems you might see with a 4-layer model. And really, so we have a northbound API from the controller. From the perspective of the controller, northbound is kind of vertical, that talks up to the applications or software, or this is kind of where the administrator might have control and create influence on the network. The controller then uses a southbound API, so from the perspective of the controller, southbound to the network elements in the data plane. The controller then tells the network elements what to do with traffic, so it sends the policy down to the network elements and can configure many network elements, immediately, and can change and adjust network elements. Also, network elements can ask the controller, hey, I've seen a new packet and I don't know quite what to do with it. So network elements can punt, decisions to the controller to ask for clarification and so forth. And so we have kind of this 3-level hierarchy here. And an example of, this concept of having these 3 layers, we can look at Open Daylight. The Open Daylight, the latest Beryllium release of this open source software-defined networking controller, we can see that up above, of Open Daylight, there are RESTful APIs. REST stands for Representation State Transfer, which is a method of using a web-based interface to talk to the APIs and set values and control. And it lends itself to, programmability in software with programming languages like Python or other tools. So that's kind of the northbound API, is this RESTful configuration. We have a controller here in the middle that has lots of capabilities and lots of functionality. And then southbound from the Open Daylight controller, we have OpenFlow, we have OVSDB, Open vSwitch, NetConf, Lisp, BGP, there's a ton of these, protocols, XMPP, other types of protocols that are southbound from the controller that then speak to the switches. And the switches can be OpenFlow devices, Open vSwitches, OVSDB devices, virtual switches. And so this is an example of what we're talking about, an example of a controller here. So by separating these layers, we get some benefits. We get greater span of control, network analytics and response. We get this central view of our network that we've never had before. To understand how traffic was forwarded on our networks previously, you had to go to each network element and inquire what they're seeing, what networks and traffic may be passing through them. Maybe we get net flow traffic from network elements sent to a net flow collector, and then on that collector we get some visibility, but that's kind of after the fact. We have no ability to influence. We can just receive information from the network elements today to get idea of what's happening, but we don't have the ability to have a feedback loop about taking information about what's being seen in real time, making software then say when a network hits a certain threshold, then I want some other path to change, or I want to add new bandwidth, or I want to bring up new routers, or I want to, create new elements. The network is not scalable like cloud services are. They don't have that elasticity, that we have with cloud systems. But with software-defined networking, maybe we could get to that level. We have better intelligence in this global view of what's happening on our network, and it can be programmed. It can also, impart information about what the application needs. In the past, we had to do this with RSVP. If an application needed 5 megabits per second from this host A to host B, we would plummet through the network, and we would use RSVP as the control traffic to try and see if the network could guarantee this amount of bandwidth to this application, or a certain amount of packet loss or something. But now we have this intelligence in a controller that can do this much more rapidly. And so we can launch new applications faster. We also have simplified operation. We only make a change to the northbound API with software, and it can be distributed to hundreds, thousands of network elements. To do that manually today, you'd have to log into that many devices. It would take you a week just to put in the configuration. And by the end of the week, your application mix has changed, or your spike is now reduced, and so you'd have to go back in and change it. So the ability to automate, orchestrate, speed up deployment of configurations is really what we're striving for here. And, we're using open source software, and we're opening up the network and using open standard protocols, where in the past, when we had a single converged network device where the data plane and the control plane were embedded in the same device, we were kind of locked into one vendor. Here we have disaggregation. Now we can buy the control plane from one vendor. We can buy the network elements from another vendor, and maybe this provides more competition in the marketplace that's better for consumers, less vendor lock-in and so forth. So here's kind of some funny pictures just to describe some of the use cases. The first one here, a submarine with compartments. Creating enclaves or layers, or doing network slicing, basically this concept of dividing up our network into different compartments may be what we want. We would want to do that if we were a multi-tenant data center, hyperscale data center. We want to split it up and not have any tenant talk to each other, but we need to rapidly be able to spin up new tenants and each give them their own container. Maybe we want to separate networks in lines of business, or maybe we have data classification needs that need us to separate our networks. And today many enterprises haven't performed any kind of segregation, compartmentalization in any way. Here in the lower left, we have a spine leaf set of switches. We have a cloth architecture where we have spine leaf switches. The leaf switches are connected to the spines, and we have a high amount of bandwidth east-west in a data center. This is kind of the new paradigm. We have less traffic going north-south out to the data center, but for big data, analytics projects, modern compute, high-performance computing, we really have a lot more east-west traffic in a data center, and so a cloth architecture, provides that. But the architecture can be big. In these large data centers, you can have hundreds of racks, more than that even, and having leaf switches in the top of rack, and then having to configure those manually would be difficult. We'd rather have a controller be able to make sure that everything is configured properly, and software creates that definition, and if there's any mistake that was made, it auto-corrects. That's kind of the idea here. in the upper right, we have the classic fish diagram. You know, we have these routers, and we have this alternate path down below that goes through R6 and R7. And even though it's farther from a hop perspective, our traditional IP routing protocol would determine that the path through R3 is the best path to get traffic east-west across this network. Well, if we use modern IP routing protocols, the path through R3 would become saturated because that's the computed best path. The routers wouldn't take into account that there's this completely unused but perfectly valid path through R6 and R7 that could be used as an alternative. But the routers don't have that global visibility, so they each just do what they know how to do based on the control plane they have today, and it ends up there's applications that aren't being satisfied, and they could be through an alternate path that's being, you know, paid for. So this concept of doing traffic engineering, software-defined networking, becomes a little easier than it has been in the past when network elements were configured, you know, statically and manually. In the lower right here, you know, today, if you created any kind of security policy, a firewall policy or something, it's an if-then-else decision tree. You know, the first entry in that access list or firewall policy that matches the packet, that's the action that takes place. And it's kind of a fall through, if then else, and there's a default, you know, fail-safe stance that if the packet falls completely through the policy, it's a deny, you know, denies the packet and drops the packet. Well, with software-defined networking, now we can change that paradigm. It doesn't have to be an if-then-else list. Maybe we could have networks that match on traffic based on Boolean operations. This kind of packet or this type of packet, but not this, or I want this kind of header and this kind of header, but not this other header. So maybe we would have other special forwarding options available to us that we haven't really thought of, haven't really conceived, and we could use Boolean logic now to define how packets are matched and forwarded and routed rather than just simply based on the destination address in the packet that the router uses to look up in its forwarding table and then make a forwarding decision. Maybe we have more flexibility here, and software unlocks that. In other use cases, you know, up here in the upper left, you know, all these types of DevOps automation tools can now be used to create and configure networks in ways we could leverage, you know, software that's been written in open source, that's been put on GitHub. We can use Python programming language to automate and talk to these RESTful APIs. We can use these common DevOps tools to now configure networking. And that's kind of something we could do. We don't have to go all the way to this futuristic concept of software-defined networking. Maybe as an interim step to adding some software configurability to our current hard network devices is simply just using network programmability and using these tools to influence our network. And we get some benefit from even just doing that one step. Up here in the top right, you know, maybe we have switches that are forwarding traffic, but maybe we want to copy the traffic and send it to a web application firewall or some other kind of probe or security function or DDoS packet scrubber. Or maybe we have network devices today that have limited number of span port mirroring ports, and we really want to do some more things with our traffic. So maybe we want to copy the traffic, not just copy it once, copy it multiple times, and then send it to some advanced analysis, and then based on that analysis, have that analyzer talk to the controller and then change the behavior based on what it's seeing in real time. Maybe there's ability to change the way we do network taps or how we do analytics on the data that's being transferred across the network. And then in the bottom middle, you know, cloud-based networking and how to set up networks that are virtualized in a sense that geography has no meaning. But we typically use IP routing protocols today, and the address has some representation to the geography of the location in its network topology, but we want to virtualize that, and we really want to change this. And so with software-defined networking, we have the ability to kind of turn things on their head a little bit. Here's a Cisco slide that kind of talks about this idea of automation leads to programming, leads to improved efficiency of the network administrators, gaining some OpEx savings. You know, now we have optimization, central intelligence in the controller, and now we can have some more knowledge of application traffic and current traffic patterns and change the way the network behaves to improve application and end user experience. Now we have some better OpEx savings, increased end user productivity, applications are optimized. Well, we just want to do some simplification, abstraction, looking at application uptime or monitoring end user satisfaction. We can do these things with a software-defined networking where we couldn't do them historically. So now that you have an idea of what software-defined networking is, the concepts, now let's talk about who in the industry is working on software-defined networking. There's a variety of industry standard groups and foundations and consortiums that are working on software-defined networking. I think one of the more popular ones is the Open Networking Foundation, the open group that has many vendors support to create this concept of open flow, which is that southbound protocol that's used from controllers like Open Daylight to talk down to network elements. And they have their standards, and you can go to their website to read about open flow. Open flow is that southbound protocol of putting flows into network devices, and letting network devices, then query the controller and ask for clarification on how packets should be forwarded. So it's kind of a southbound protocol there. The OpenStack, foundation, creating a private cloud platform to be used that can automate creation of cloud environments for multi-tenants. It has networking and software-defined networking built into its orchestration systems. Open Daylight, part of the Linux Foundation, creates that Open Daylight open source controller that many vendors contribute to. And then many vendors then also have for sale versions of supported versions of what they've contributed to Open Daylight too, but Open Daylight is an open source package software system. The IETF has a bunch of working groups focused on software-defined networking and how IP networks can be programmed or changed or automated. And the ETSI, ETSI organization as their network function virtualization group, defining how networks virtualized and how functions are virtualized inside of this network fabric. So a few industry organizations. So, this all sounds great, software-defined networking, but there are some challenges, and the industry is working to overcome these challenges or overcome them in some cases. I think early on in software-defined networking, there was that concern that, well, what if my controller goes down? Well, then is nothing flowing across my network? Well, now we have, redundant controller architectures. We've, sharded the database, sharded the intelligence across multiple controllers. So we have other functions separated. So if any one controller goes down, we have redundancy, kind of like raided and used RAID as a model of sharding the data and the intelligence across multiple controllers. And, what if we have just a single central controller that had to be notified of any failure? Well, there's latency between wherever that network device is and that controller. If our controller is on the West Coast and we have network elements on the East Coast of the United States, then it could be latency and it could be a long time to adapt or get information and speeding up of the latency. Well, now we have redundant controller architecture, so we can have a controller on the East Coast and controller on the West Coast. But these can be challenges for SDN in some ways. And also just speed of creating flows. The network elements get lots of application traffic. Imagine a really popular website or an online retailer gets, hundreds of thousands of hits per second, million hits per second probably during their, peak season, maybe before the holiday season, and the flow setup. So can the controller keep up with the number of flows per second of new connections that customers may generate to a web application or something like that? And then vendor interoperability. I think the vendors see that the controller is another form of vendor lock-in. If you lock in with a vendor's controller and you use that exclusively, and you write a lot of software and custom software to their APIs, you're less likely to move to another version, another vendor's controller maybe. So some current vendor solutions have some proprietary openness. They may be using, open standards for southbound and northbound protocols, but if you're using their APIs, you've kind of, in some ways, locked into a controller architecture. How do we use SDN on the internet? I mean, today we use BGP, that's the control plane protocol on the internet, and it's scaled to a really high degree. But how do we get this software-defined networking functionality to work on the internet? Difficult to convert the internet from IPv4 to IPv6, much less move from BGP to something else. I think it's still early days here, right? Human factors. I mean, if a human can make a mistake configuring a network element, a human could definitely make a mistake configuring a controller. But hopefully we have a little bit more, checks and balances in place with the controller. And software-defined networking kind of transcends IT groups and silos, and so if groups don't work together well today, they won't work well today in a software-defined networking world. If your security is lacking in your current on-premise data center, when you move to the cloud, your security could also suffer as well. So just human factors play a part in all of these things. Some people could say software-defined networking is an unproven technology. The industry is in its infancy in some ways. Many small vendors, many different types of protocols jockeying for position. I think we'll still see, over time, vendor consolidation and these ideas, the best ideas will be weed out over time. Current IT staff often doesn't have a lot of time to get up to speed on new technologies. They're spending a lot of their time maintaining the current investment in IT infrastructure and systems and software and supporting, and so they have less time for net new projects like software-defined networking, even if it does have a lot of business benefits. And it's difficult to prove an ROI, total cost of ownership analysis. You have network devices that have already been capitalized on, already functional. Difficult to say I'm going to invest in something else or I'm going to completely replace my existing network infrastructure to obtain these new features and capabilities. It could be generational, and as hardware refreshes out of the environment, as old switches get upgraded to, from 100 meg, 1 gig switches get upgraded to 10 gig switches, that's maybe a compelling reason to look at a software-defined networking system, for example, or when you're doing a data center upgrade. And then there's security considerations. This is just kind of a teaser for a presentation that we'll give in a few months as part of this SDN webinar series. We'll talk about software-defined networking security. So what do we need to consider in terms of making sure our software-defined networking systems are secure, but then also what kinds of things can we do with software-defined networking to help make our environments more secure in ways that we have difficulty doing today. So I talked a little bit about the operational model. Really, I think network, security, DevOps teams need to come together, not just for DevOps or DevNetOps or DevSecOps, but we need these groups to work well together to gain added programmability features to speed up continuous integration and deployment of applications. The network and security teams are instrumental. And so many network and security administrators may be fearful that this could threaten their jobs or threaten their position or their usefulness. But the reality is that what network administrators, security administrators, systems people know are all very valuable to the company and can be leveraged. And I think maybe there's an opportunity here to streamline what you do, automate many things that you do manually, and buy back time to then, for more creative pursuits about how you could use a network or security systems to improve the business or defer risk for the business. Operational issues can sometimes arise in software-defined data center environments where groups don't work well together. So they're used to that Ethernet demarcation between the load balancer and the switch or the firewall. they're used to that Ethernet port defining, you know, their roles in the demarcation of you do this, I do that. And now that we have a virtualized firewall, a virtualized switch, a virtualized network element, a virtualized load balancer, groups have a tough time kind of overcoming this. And in some cases, organizations don't work well together, and even if the technology is feasible and possible and deployable today in a production environment, it prevents them from taking advantage of some of these benefits because they just can't figure out how to work together and cooperate and collaborate to get some of these benefits to the organization. So these silos of IT operations sometimes don't lend themselves to network function virtualization or software-defined networking. I've got a question here about what I just mentioned about Boolean logic. Comment I had made about Boolean logic and are there performance hits to that. Yes, traditionally when, you know, matching against a packet where it was a big if-then-else tree, you know, you'd match it, but there are, you know, that you would look at each route and then decide, you know, statically top-down which matches and then forward. But today, network devices do hashing and other techniques to determine the next hop, and they do this quite rapidly in hardware and have hardware acceleration and use FPGAs and ASICs to speed up matching and deciding yes, no, forwarding. And so these ASICs are really fast, and you can put some of that functionality into the hardware to speed that up, so it can be just as fast as, you know, traditional forwarding. It doesn't have to be process-based. And then flow setup, there can be latency in flow setup if the controller isn't optimized, if the controller is very far away from network elements, but they tend to be joined together in the same data center. You know, you have a data center environment with network elements, and there will be a controller localized or a set of controllers that are redundant and localized, so decisions can be made very fast, and flow setup can be very fast today. And also just with Moore's law and speeding up of processing power can improve things. Also, in the past we had network elements which had very small processors, and they had to make these control decisions. Now we're using x86 processing and compute power at the edge of the network to make these decisions. So we're able to even do more because we have more compute capacity available in our servers today than we have in network elements historically. And so speeding up in the latest, you know, Intel chipsets and the integration of networking into those Intel chipsets and the conversions of networking and servers, now the lines are blurring on where's the server, where's the network, that we're able to leverage more compute power on the edge to make these forwarding decisions faster. So really good question. Hopefully I answered it. And so just from an operational standpoint, if groups don't work well together, they may not work well together when you move to a software-defined networking system. So we really want groups to be cross-functional to take advantage of all of these benefits. And we need groups, you know, we need DevOps team to be able to help with, you know, automation. We need network engineers to explain to DevOps teams why we want networks built in a certain way and why avoiding loops with spanning trees is important. And we need security administrators to help determine what's the proper application policy to meet our compliance requirements. Every group is necessary and required, and if they work well together, I think business benefits as a result. So, I mean, there aren't as many software-defined networking deployments in enterprises. Sometimes, you know, people may be wondering, well, who's using, you know, cloud, who's using software-defined networking, who's using network function virtualization, and so people may be confused about where SDN deployments are taking place today. Definitely universities and campuses doing campus slicing and other advanced networking research are taking advantage of software-defined networking. Absolutely, the hyperscale, multi-tenant data center environments are using software-defined networking? They have to, based on the scale with which they're operating. They have to have software automating these. Can't have an individual person manually configuring these things by hand because of the density and just the vast volume and scale, the web scale that they operate in. They have to have software-defined networking. Some organizations that require TAPs to do advanced data analysis, maybe using software-defined networking just for some simple copying of packets, where they might have traditionally used a matrix packet monitoring switch. They may be doing this with network devices. And there are some enterprise data center deployments that exist. And we're starting to see some software-defined networking in the WAN, with hybrid WAN architectures where you have a controller that's deciding for a branch or a store or a remote site how and when some application traffic from that branch would use an MPLS service, a internet service, or a 4G, LTE service, and so forth. So you're seeing some software-defined influence in the branch. You really see software-defined you have a controller, a wireless LAN controller today in your environment. That's kind of this controller architecture in a sense. That's an example of some software-defined networking or of a software-based controller pushing out configurations to the WAP. And so we're starting to see, enterprise deployments within data centers as well. And we'll definitely see more SDN deployments emerge as these solutions mature and as organizations are up for maybe hardware renewal, or they're expanding, or they're moving to the cloud. That'll be a time when they probably revisit their network architecture and investigate whether software-defined networking can unlock some benefits to the business. We'll definitely see consolidation in the vendor space. Some vendors, may not make it. Some vendors may be, acquired by larger vendors. We see the large vendors definitely, they're not going to let their existing businesses be disrupted. They are at all the large incumbent network equipment vendors have all participated in, these industry standard groups, building software-defined networking controllers, working on multiple controller architectures to hedge their bets in case one maybe doesn't play out in the industry. And I think these larger vendors see, the controller as a way to get some, stickiness with their customers and a little bit of lock-in. And these standards are continuing to emerge as these standard organizations evolve the protocols that are used, both for southbound and for northbound. So a bit about GTRI. We have this virtualized and advanced networking professional services group that's focused on these SDN solutions. At GTRI, we work with many leading network solution vendors and top-tier partners, and we're learning about their solutions and helping our customers adopt them and understanding how they could adopt them for maximum benefit. We perform these software-defined networking readiness assessments for our customers to help them kind of assess where they're at, what benefits of software-defined networking, can they realize given their current equipment, staff, skills, teams, goals. We have a test bed in our laboratory where we're doing lots of testing and validation, and you're welcome to work with GTRI to test and validate as a proof of concept your deployment. Certainly you would do that well before a production deployment. And we're performing software-defined networking implementations for customers, and so we can share with you what we're learning along the way. At GTRI, we have a global services framework methodology. Starts with kind of understanding our customers' vision and needs, understanding what are the capabilities of software-defined networking, or what are their applications, or what are their goals, going through a design phase, really setting up for a successful deployment. And then once a customer may have a software-defined system implemented, then talking to them about how they could evolve that and expand upon that infrastructure to release even more benefits to the business. So we follow this methodology for all of our professional services engagements, and we kind of look towards this methodology of how we would go about creating and deploying a software-defined networking system, right? There's goals and ideas and vision of a software-defined networking system. There are a lot of technical details to help guarantee project success and to precisely deploy an SDN system, but then also confirm the functional testing and verification that that system is performing as we expected, and then understand how we can do even more with that software-defined networking system after it's deployed. So if you're interested, we offer a free SDN workshop, technology review for your company. If you're interested, we encourage you to bring your teams together, the networking, security, DevOps, other technology teams together, and we can have an interactive workshop to talk about software-defined networking, where you're at today, what your goals are, what are your initiatives, what kind of a software-defined networking system might work best for you, what are the different options, what are the different protocols, why you might choose one over another, and we can bring our SDN experts to this workshop to help you kind of understand what you could do with software-defined networking, review the capabilities, because maybe there's even capabilities within your existing network infrastructure, help you kind of plan what the high-level roadmap would be going forward, and just answer any questions you had about SDN architecture and design, and go through and review how you might even take advantage of some network automation and programmability in the near term. So with that, that ends kind of what we had prepared for the slides and the presentation format. I was wondering if there was any other questions people had. I didn't see too many in the chat panel, but if you have your questions, you can go ahead and enter them into the chat window. So let me know if you have a question. Okay. So I see one question here. Question is, if I am an IT engineer, do I have anything to worry about with the introduction of SDN? Should I be afraid that this will eliminate my job? So I think this is a common concern about, whenever software or robots get involved in the world, we're concerned about a Skynet formation, and now we're obsolete. Didn't someone say that humans are basically just bootloaders for the robots? We are the wetware for, to help the robots achieve superiority. Well, I don't think that's the case. I think that what network engineers, what IT people have spent decades understanding and building is transferable to a software-defined world. Certainly, a programmer couldn't just program in how all this works. They wouldn't know what to program. So I think the experience that IT staff have, network engineers, security architects have about their organization and about how they need to, secure or network or connect their environments is valuable and transferable. And it's not a situation where the network engineers have to become programmers to stay relevant. I think you could, as a network engineer, leverage software that's already been written and published in the open source community. You don't have to be a programmer to really adapt or download something that you get off of GitHub, modify it to be usable, and then and then take advantage of that, as a benefit to the business. We did have one question here, how much programming, coding, scripting knowledge is needed to make the move to SDN? Some, but it may not necessarily be you who's doing the coding. Maybe there are folks within your organization, your DevOps teams, that already have those skills, but they just don't know enough about the networking layer to make any changes or do any automation. So I think organizations that glue together their teams, that combine the best of their DevOps teams with the best of their networking teams can realize this. But one team couldn't do it without the other. And so you may not need to program or script. I definitely encourage that because I think it's valuable to know enough to be able to then talk to the DevOps folks about how an application may be built to then control your network. but you certainly wouldn't want a DevOps person or a software developer doing this without your input, right? So what you know about networks, your environment, and your systems definitely valuable and transferable to a software-defined world. Another question here. Is it going to decrease the amount of knowledge needed to be a network administrator? Is it going to turn everything into a point-and-click network administrator? I don't think the controllers are advanced enough where you can just make them that easy to configure. The controllers are fairly complex, and so they need a lot of configuration, and that requires a lot of knowledge about networking and systems. And so I think people in an organization, an IT organization, become more valuable the more different domains they know. So if you know about server and server network virtualization and networks and security, you're more valuable to an organization than someone who just knows about, IP telephony or something like that. If you are more cross-functional, I think that's what you would like. I think it's good to know about multiple disciplines and be able to at least know a little bit about what the other team needs to achieve. And I think businesses want their teams to be cross-functional. I know GTRI, our customers, expect our consultants to be cross-functional, multi-domain experts, because anything you do in IT today crosses those IT silos. Let's say you go to deploy a NAC system or something like that. You couldn't deploy that without integration with security, without networks, desktop support, systems. You couldn't deploy a wireless network without crossing domains. A wireless LAN crosses desktop support, network, security, they're really cross-cutting functions now. So I think what you know is really valuable. Now, I think if you didn't continue to evolve your career, I think you could get caught in a position where you might not be invited to those meetings. If all you do, but I also tell security administrators, if all you do is take and add firewall rules to a firewall, or if you're a network administrator and all you do is assign Ethernet ports to VLANs, if that's the extent of your job, I think you are likely to be programmed out of the equation. But I think it's easy to become cross-functional and work to learn more and ensure your relevancy in your IT organization. So I encourage you to learn about these concepts we talked about today, bridge across your IT silos that may exist to become cross-functional, and I think you'll see your career benefits as a result, and what you know is valuable to the company. Well, I often get this question, does OpenFlow support IPv4 and IPv6? It does. OpenFlow started to get IPv6 capability in OpenFlow 1.3. There are some OpenFlow controllers that still only support OpenFlow 1.0, 1.1, so those wouldn't have IPv6 capabilities. But modern OpenFlow switches and controllers that use OpenFlow 1.3, 1.4 definitely support IPv6 and can match on any IPv6 header value. So, yeah, thanks for the IPv6 question. My favorite topic. Any other questions? We just have a few more minutes here. Here's a question that just came across. What are some good ways to start to learn more about SDN? I think there's a lot of great resources on the internet. I'd encourage you to go to the websites of those open source, open standard organizations that I referred to, learn a little bit about. I think you can download Open Daylight for free and start to experiment with that. You can download Mininet. There are some really good Coursera classes available on software-defined networking. And there's a lot of resources now on Python programming, so I encourage you to maybe learn about that. It's a very easy programming language. It's very fun. It's very natural language programming language, so it's not difficult. And there are a lot of low-cost or free resources on the internet to learn about that. So here's a question. Does the cost of implementing SDN scale to the size of your business? Is it feasible for smaller businesses or small network environments? Yes, it's all relative. I think you can, and maybe there are definite cost benefits to smaller organizations for disaggregation. Now you have more flexibility to choose vendors. You might choose a switch hardware, a network element hardware that suits your budget and suits the number of ports you need, and maybe then you could leverage an open source piece of software, and with some of your time and effort, you could build a system that's as robust as what a large enterprise would spend far more to get. So as a small business, you might have the ability to be more agile and flexible and use cloud-based services, and SDN and would be congruent to those ideas of keeping your costs low. So now you're not totally tied and locked into a large vendor that charges a premium for their network device. Now, through disaggregation, you have the ability to keep your costs low. Okay, so here's my contact information. So if you're interested in setting up one of those SDN workshops, please reach out to me or any one of the GTRI team members, and we can work to kind of set that up and get that organized for you. Again, you'll get the slides, and we recorded the session today, so you'll be able to watch a replay. If there was something I said that didn't make sense, please reach out to me. I'd love to clarify it for you. So with that, I think we're concluded for this SDN web seminar. Look on GTRI.com for future software-defined networking web seminars that we'll have in the coming months, and other events that GTRI maybe have coming up that you might be interested in. Okay, so with that, we'll go ahead and close the session. I hope you all enjoyed it, and I look forward to talking to you more in the future. Take care, everyone. Bye.